This video we will talk about transient response characteristic or transient performance for higher order systems. Let's assume that we have transfer function g of s. Okay, it's a closed loop system. We have constant. Okay, so let's call it like k, but the technical polynomial has two poles. Okay, s squared plus a s cubed plus a squared plus bs plus c. So we have three poles. So what happens? What we can do in order to talk about transient performance and transient characteristics. Okay, so what we have, let's remind all of you, setting time, overshoot, okay, peak time associated with overshoot, and the rise time. We already know that setting time and overshoot are more important, and peak time and rise time somehow more related with the underdamped response. Okay, that's guys. We have technically three poles for a third order systems. For a fourth order system, we have four poles. And let's assume that for a third order system, we have following pole locations. Okay, that's nice. Okay, so what we can do? If you remember, for an overdamped response, when computing the setting time, we use the pole that is closer to the origin. Okay, this is the basic idea. If this distance, okay, so let's call it sigma 2, and sigma 1 is sufficiently large, let's call it 3 times the sigma 1, and it really depends on the system. We can technically approximate this system as a second order system, and we can ignore this pole, okay? And this is called a second order approximation or dominant pole approximation. So why we did this? Because we know that this pole has an exponential, okay, e to the power minus sigma 2, that is technically much faster than the second order pole, such that it will go to the zero quickly, and after some time, which is relatively fast compared to the time scale of these poles, the system will look like a second order system. So by just using these two poles, we can compute setting time, overshoot, peak time, and rise time. So this is the basic idea, and we can do it not just for third order systems, we can do this for higher order systems, such as, like, say, we have two poles here, one pole here, and something like that. In general, okay, the poles that are close to the imaginary axis dominate the behavior. Okay, and this is especially true if the poles that are closer to the imaginary axis are complex conjugate. Okay, this is the only thing actually that you need to really remember about dominant pole approximation. Okay, let's talk about different cases. Okay, and let's assume that we have a single pole here, okay, double pole or complex conjugate pole here. So we have a similar story, but now the pole that is closer to the imaginary axis is real. The poles that are away from the imaginary axis are complex conjugate. So what about setting time? So we know that these poles associate, the exponential associated these poles will be like e to the power minus sigma 2 t. Of course, we will have some sort of sine omega dt. Okay, that's nice, we know that. But still, the sigma 2 will be larger than sigma 1. Okay, in that respect, this will go to 0 much faster than this, and we can approximate the behavior as a first order system to compute the setting time of the system. Okay, that's nice, we can do that, that's great, and it makes sense. For a computation of the setting time, what we can do is we can always use the pole that is closer to the imaginary axis as a good approximation. Of course, the level of approximation depends on many aspects, how close other poles are, what is the numerator dynamics, and other kind of effects. But what about the overshoot? Okay, so can we say that the overshoot is equal to 0? Of course it's not, because we know that the existing of these poles, we are guaranteed to have some sort of overshoot or some sort of oscillator behavior. Because if I draw the response, okay, it can look like this. I don't know. Okay, so let's assume that it has a very quick setting time, but it like oscillates a lot. It's possible to have this kind of behavior, especially for higher order systems. Okay, so if we compute the setting time, this can give a good approximation, but we cannot say that the overshoot is equal to 0. So in this case, what you can do is you can use the pole that is closer to the origin to compute the setting time of the system, okay, and it will generally give you a good approximation. You can use the complex conjugate poles that are closest to the origin to compute the overshoot, peak time, and rise time. But make sure that, or at least I want to remind you that if you do that, they will give you a guidance, some numbers that can be used to design some characteristics that could be fine, but expect a high level errors compared to the classical second order system. You can still use the poles, complex conjugate poles that are closest to the origin compared to the poles to compute overshoot, peak time, and rise time. For example, let's assume that we have a scenario like this. Okay, for a higher order system, we have a plot where it is very close to the origin. We have two complex conjugate roots here. Okay, we have a real root here. We have two complex conjugate roots here. Okay, so in this case, what we can do is we can use this pole to compute settling time. Okay, that's great. And we can use these two complex conjugate poles to compute overshoot, peak time, and rise time. Okay, but again, if this is closed, this will give you a good approximation, but there will be some errors. But if you use these poles to compute overshoot, peak time, rise time, expect errors in the order like 50%, and it really depends on the system. For Samsung, they can be very good. For Samsung, they can be very large. But in general, what you can be sure that if the poles that are closest to the origin are complex conjugate, and all poles are around here, and if there's a good distance between them, you can make a dominant second order pole approximation if it's over them, and then you can compute settling time, overshoot, peak time, and rise time. But as we told you before, these formulas, especially the settling time, are true first of all for the standard case where we have constant numerator dynamics. Okay, and some of them are even approximate, such as settling time, even for the ideal case. Okay, if you simulate the response, you can get different results, and we generally use this as a design guideline. If you have hard requirements for your transient performance characteristic, you always need to do some sort of simulation to make sure that everything is fine.